We use the letter I for current. I always represent the current. I is equal to change in Q. Q here is the charge over change in time. Change in charge over change in time. Because Q used to mean heat for us before in one of the previous chapters, so here Q is charge. So basically what current is, if you have a wire and you plug that wire to the wall, and you let's say you have this plugged into the outlet there, and the top of the wire is made out of glass, and you can count how many electrons are going through that. If you count how many electrons went through it per second, we know what the charge of each electron is. That's what the current is. The number of charges, the amount of charge that went through that little opening in 1 second. So if you know there's, for example, 10 electrons went through it in 1 second, then the current will be the change in the charge over change in time. We know the time was 1 second. And what was the change in charge? 10 electron, I counted 10 electron going through it. Well, each electron has a charge of negative 1.6 times 10 to the negative 19. So you do the math, that'll be what? Negative 1.6 times 10 to the power of negative 18. And that's coulombs per second. Well, instead of coulomb per second, we use A for ampere. Amperes. So we measure the current in amperes. 1 amp equals 1 coulomb per second. Now, when you have a flashlight at home, and the way the flashlight really works, this is how the flashlight works, is you got the top of it, you get two batteries sitting on top of each other, usually, like this. That's your voltage here. You have a wire that's attached right there. You have the bulb, which is right here. And you have a wire, this is sitting touching here, and you have a wire attached right there. And what you have a switch. That's what the handle is. When you push that piece there, you close that switch and you make contact, you allow the current to go through it. And as the current goes through this, it heats that element and you see the light on the flashlight. So we can make a flashlight, just take two batteries or even one battery, take a bulb, put on the top, take a wire and wrap it around. And you'll see the light goes on. If you use one battery, it's not a bright. If you use two, it's brighter. If you use three, much brighter there. Now, that's how that works. When we draw that, you'll see that we're not going to draw it like this. This is a voltage source. We'll talk about that in a minute. The battery is a voltage source. And we're going to talk about something called resistors. These wires have resistors built in them. So is this one right here. So we're going to bring in some terminology here. But that's what your flashlight basically is. You have a voltage source. We don't draw it like this. We have a voltage source like that. And if you put two batteries of 1.5 volts here, so you have a voltage source of what? 3 volts here? Because there's two of them on top of each other. You get that switch that's in your hand to open, close, turn the light on. And what you have the bulb right here. That's how we draw that. So when you push that little thing to turn the knob on, again, you close this one and you allow the current to travel through that. You're allowing the current to go through that. So that's my voltage source. Again, instead of the battery, we'll use that symbol for voltage source. So voltage here, we'll talk about a lot of things here. We're talking about DC source, DC direct, that's constant value. So a battery here has a voltage here. If you take a 1.5 volts, I'm going to draw that as a voltage source like this of 1.5 volts. Notice the little piece was one long, one short. The long one is the positive, the short one is the negative. Sometimes you see me do two of them. It doesn't mean twice that. It just sometimes I use one, sometimes I use two. Still 1.5 volts. The minus is the short one is the minus, the long one is the plus. So if I have a 9 volt battery, I'll draw that like this, 9 volts. If I got a 6 volt battery, I'll draw that like this, 6 volts. If I reverse the battery, put them upside down, if I take a 6 volt battery, which is like this, then if I flip the batteries, it will look like this, and that voltage is no longer 6, it becomes what? -6. So you can flip that voltage to a positive, negative. What that means actually doesn't mean, it means this end is 6 volts higher than that end. That's what that means. This end is 6 volts higher than this. I do have actually a voltmeter here. It's still here. Hopefully it's working. And it's missing today. Let's see if we move down. Nope, it's missing now. Maybe I moved it, somebody moved it. Oh, it is moved, yep, I can feel it. I don't know if the battery is good or not. I'm in trouble because I just put on voltage and it's dead. Damn it. Okay. I gotta see if somebody has voltage here. Batteries to measure. It looks like it was on voltage the whole time, so it wasn't shut off. But this one actually is called a multimeter that will measure the resistance, the voltage. If anyone has little batteries like this I can borrow, I can give them back to you.
Probably not.
Nobody has them. For any devices, maybe. Let me see. No, wait. I still have something. I might have. I have a laser pen. Where is it? If I still have it. I don't know if there's actually. Oh, there's two of them. Let's see if they work. I don't know if they charge or not. They could be dead too. Nope, they're dead too. Figures. I don't know quickly if they're dead. I'm sure they're dead. Rush. Hell with it. I put it sideways now, it doesn't want to come out. But I can measure the voltage. This is what will happen. If I take two batteries, so we're going to talk about the voltage here. If I take this battery here, sometimes you guys see him. And I wish that was working because I can show you the number. I see somebody with hearing aids who can take their batteries. Notice this is a battery here. This is actually marked plus minus. Can you see it? Plus minus. There's a plus and there's a minus down here. Can you see the plus side? So on your, this is a 1.5 volt battery. So when you buy it, it's really 1.5 volts. If I take another one and put it on top of it in the same direction, and I put another 1.5 volts on top of that in addition to that, So if I was to measure the voltage between the top and the bottom, right there, what's that value will be? 3 volts. Now if I reverse this one, and I put one down, one up like this, so this one basically is reversed now, the top one. So the minus on the top, the plus on the bottom, like this. This is 1.5, this is 1.5. Here's what it means. If this is attached to the ground, this is ground, that tells me this end has to be 1.5 higher than this. So this end here should be 1.5. And the way this is set up, this is the, notice the longer piece, it says this end is 1.5 higher than that. So this will have to be what? 0. So if I measure between the top and the bottom, I should read 0 voltage. They cancel each other out. So you can take voltage sources, if they point the same direction, add them and make one value equal to either the sum or the difference of them. Now, when you connect things like this, we'll talk about this, that's called connected in series, the way you see these two. I'll add that to the list here. When you take an element like a source, like a battery like this, and attach to it another battery like this, that's called connected in series. And because this is 1.5 volts, this is 1.5 volts, the result will be, that's equivalent to having one battery of 3 volts. You can add them. The problem happens, and you probably encounter that problem along the line. You come in, I'll do this actually, instead of 1.5, you come to start your car, and your car, by the way, the battery in your car is how many volts? Isn't that 12 volts? You have a plus here, and you get the minus in your car. And it's 12 volts. But you come in that day to start your car, it won't start. Why? The battery is dead. Dead doesn't mean it's 0 volts, but it could be 4 volts. Not strong enough to get it going. But it's not starting the car. So what do? You jump start your car. How do you jump start your car? You take a good car that's running, and you attach what? The plus to the plus, and you attach the minus to the minus. Now what you did is like taking 2 batteries like these. One is 1.5, and the other one, or one is 12 and one is 4. And you attach them what we call in parallel. You put a wire there, and you put a wire here. That's called parallel. That's not good. When you have elements in parallel there, they have what? The same voltage. How can these two have the same voltage? This is 4 volts, this is 12 volts. So what's going to happen, this one is going to force this one, increase the voltage in that, and make it go higher to get your car started. If you leave it connected for a long time, this will die too. This will suck all the juice out of it. So now these are connected in parallel, and if they are in parallel, they have the same voltage. So you never want to take different sources and connect them in parallel. You don't want to put 5 volts here and go, let me attach another 3 volts to that. That's not acceptable. Because ideally, this is called an ideal source, supposed to have 5 volts cross it. This is supposed to have 3 volts cross it. But they are connected in parallel, must have the same voltage. How can it be the same if one is 5, one is 3? So this is not good. You can attach them in series, that's okay. This is parallel here. You can have a 5 volts here, and you can have a 3 volts here. That's okay. That's connected in series now. Parallel, they have the same voltage. Series, they have the same current. That's okay. And the net result of that will give me that's equivalent to having a source in this case of what? 8 volts. 5 plus 3. So that's the voltage source or voltages. Now we know what current is, we know the voltage here. And what about resistors? Next one I'm going to talk about is called resistors. We'll either go to the lab today or tomorrow. And I'm going to show you resistors. Now, if you look at them, they're probably about 1 centimeter long. They look about this big. It's a little round thing with the wire sticking out of it. And if you look closely at these, they'll have actually usually 3 or 4 lines going through it in different color, wrapped around. And those actually color, we can look at them and tell you what the value of that resistor. The first digit, the second digit, and the multiplier. And this is the tolerance, within what percent. But that's what a resistor will look like. It looks like a hard glass, actually. You can break it, and the inside of that could be filled with multiple things. The inside of that could be filled with some options here. Cortez, rubber, glass, silicon, germanium, lead, iron, aluminum, gold, copper, silver. So the inside of that could be anything. And the value of that resistor can be found by taking rho times L, the length of it, divided by area. And rho is the resistivity. That's your resistivity. As I said, it changes from substance to substance. If it's rubber, it can go between 1 to 100 times 10 to the 13. If it's glass, 1 to 10,000 times 10 to the 16. If it's lead, 22 times 10 to the minus 8. If it's iron, 9.71 times 10 to the minus 8. If it's silver, 1.59. Germanium, silicon, very small value. Cortez is 7.5 times 10 to the 17. So we can make the resistor huge, we can make it very small. So if I take a resistor, for example, a length of 1 centimeter long, diameter, let's say it's 0.2 or 2 millimeters, 2 millimeters, and I fill the inside of that, I don't know, let me pick, let's say Cortez, the inside of that. Which has a value, Cortez has rho equals 7.5 times 10 to the 17. So what's the value of that? There's a wire again going through each end. What is the value of that resistor? The value of that is going to be 7.5 times 10 to the 17 times the length of that. The length is 1 centimeter, 0.01 meters, divided by the area, pi r squared. And r is what? Isn't that 1 millimeter? Which is 0.001 squared. They convert that to meters. So this actually will have a value for a resistor 7.5, turn on, 7.5 excuse me, e to the 17 times 0.01 divided 0.001 squared times divided by pi. That's a huge resistor. 2.387 times 10 to the power 21. We measure a resistor called ohms. We use this symbol for ohms. Now, let's assume the same resistor, the same dimension now. I use silicon. But instead of Cortez, I use silicon. And I'm going to use for this rho equals 0.2. So the value of that resistor is going to be 0.2 times 0.01 over pi times 0.001 squared. And the value of that resistor becomes 636.6 ohms. Smaller value. So just because the number is big, that doesn't mean you have a massive resistor. Notice this is a humongous number. And the resistor is 1 centimeter long and 2 millimeters in diameter. Very tiny. Smaller than the eraser on the end of a pencil. That's the size of it. Actually smaller than that. And look at the value of that. And if I change the inside of it, look how small the number is. And I can even make it smaller than that if I use gold or if I use iron or gold, I can shrink that number to less than 1. Now, we call resistors because they resist the current. They block the current from going through it. So when we draw a picture of a resistor, we're not going to draw that. So the way we draw a resistor of 10 ohms, for example, this is how we graph the resistor of 10 ohms. We go like this. That's a 10 ohm resistor. We go like jagged edge. A resistor of 50 ohms or 1,000 ohm. I forgot the T here. We draw that 1,000. We just write 1,000 ohm over it. So when you look in the book in a few minutes, you're going to see shapes like this. For a resistor, you're going to see that little long dash and short dash for the voltage here. You're going to see these for voltages. You're going to see these for resistors. That's what you're going to see. Now, we have an equation in electronics. If you took any electronics in high school, you probably heard that. Something called Ohm's law. And Ohm's law says the voltage is equal to I times R. Give me two, I'll give you the third one. Here's an example. If I have a resistor of 10 ohms and I take a voltage source right there, plus to minus 5 volts, and I put across that, I'm going to have a current. Now think of the current just like water. When you have water, it goes from the top of the hill to the bottom of the hill, right? If you pour water, it's not going to go up the hill. It's going to go downhill. So the current's going to go downhill. The plus is the top, the minus is the bottom. So the current will go in this direction, I. And what's the value of that current? Well, Ohm's law says V equals I times R. The voltage is 5 volts. I'm looking for the current. The resistor is 10. What's the current equal to? 5 over 10, which is what? 0.5 amps. That's a 0.5. Next, what happens if I take that resistor now, same resistor, but instead of 5 volts, I put 15 volts. Plus on this end, minus on that end. That means there's current going from the plus to the minus in that direction. And let's see, I increased the voltage by 3 times. What do you think is going to happen to that current? Is it going to increase by 3 times? Well, let's see. Voltage is what? 15. I'm looking for I. The resistor is still 10. I equals 15 divided by 10, 1.5 amp. So I increased that voltage by 5 times. My current, by 3 times, my current increased by what? 3 times 2. So Ohm's law says if you increase the current, the voltage will increase. If you decrease the current, the voltage will increase. And vice versa. The voltage and the currents are directly proportional to each other. If you increase one by a factor of 2, you increase the other one by a factor of 2. Or I might say to you, I have this resistor. I don't know the value of the resistor, unknown. And there is 7 volts right across that, and I measure the current through it. And when I measure the current, I had a current going that direction of 2 milliamp. Can you tell me what that resistor is? V equals I times R. V is 7, I is 2 milli, that's 0.002 times R. What is R equal to? Is that 3,500 ohms? Yep, 3,500 ohms. And let's bring in one more topic. So now this is Ohm's law. We talked about voltages, resistors, current, Ohm's law. Let's talk about power. As I said, I teach this in about 2 months. I'm trying to give it to you in an hour. So I'm only going to give you the stuff you need to know. Power. If you remember from physics, power is the amount of energy per time, basically. Power here is defined as, or you can calculate power by taking the current times the voltage. And we measure power in watts. That didn't change from James Watt from before. But if I use Ohm's law says V equals I times R. Or I equals, if you look at it, V over R. That's Ohm's law right there. So if I take V and replace it with I times R, so this power, this is correct. But I can also do a substitution. I can say it's I times, in place of V, let me put I times R. And I end up with power equals what? I squared times R. So if you know the current and the resistor, you can calculate the power. If you know the current and the voltage, you can calculate the power. You can also calculate the power if you know the voltage and the resistor. Here we go, the third one, power. It's I times V. What is I equal to? Isn't I equals V over R? times V, which is what? V squared over R. So power can be calculated three different ways. Depends what you know. If you know the current and the voltage, you multiply them. If you know the current and the resistor, we use that. If you know the voltage and the resistor, we use this. So power, finally, is equal I times V, which is also equal I squared times R, which is also equal V squared over R. And the units for that are watts. Okay.